Today we are going to discuss the first two sections maybe of chapter 18. So we will see as we go along. Okay, so chapter 18 will be talking about the multivariate 1 and 2 sample models. And this will be focusing on the inference about the mean. No? So inference, it means that we will be talking about estimation and hopefully hypothesis testing on the mean vector mu. So recall that a multivariate one sample model, we start with a one sample model, is one in which we observe we have some y sub I1 to yn, y1 to yn independently, identically distributed. So this is IID. Are dimensional random vectors such that each of the yi's here are normally distributed with a mean mu and a variance sigma. So this is the scope of the mean can take from negative infinity to positive infinity, but your covariance matrix should be positive definite. Note that we are assuming the distribution of the yi to be non-singular normal distribution. That is, we assume sigma to be positive definite for it to be invertible and the inverse of sigma exists. This model would occur if we had R measurements, example, height, weight, and income on each of the n individuals. So in this chapter, we primarily concerned with inference about the mean vector mu. So since we will be talking about estimation, the first thing that we should look is the estimator. So the most common estimator, which is considered to be very useful, is the sample mean y bar, which is computed as the usual formula, the sum of yi's from 1 to n, then divide it by n, and your s. So this is sigma estimated by s. So if this is your parameter, this is estimated by theta hat. So in this particular scenario, this formula here with the denominator or this term divided by n minus 1 will be s. So, or ang usual dapat ani is s square, but Arnold just uses s. Mao man na ato ang ginagamit sa univariate case. If we have sigma squared, this is usually estimated by s squared in the univariate case. But in this scenario, in the theoretical multivariate case, they use sigma and it is estimated by s without the square there. But the formula is the s only, no? Because usually we use s square because for the standard deviation, it is denoted by s. So this time, the standard deviation will be the summation of s, no? Summation, the square root of s. Anyway, that is just notation wise. So consider this estimator y bar and consider this s as an estimator for our sigma, and we see that these two are jointly sufficient statistic as well as it is a complete sufficient statistic, and we will look later on its distribution. So what will be the distribution of y bar? Is it normal? No, it's normal if given that the yi's here by assumptions are are normal. So if the yi's are normal here, what will be the distribution now of your y bar, wherein it is a transformation of the yi divided by n? And what will be the distribution of s having a transformation squared quadratic form, no? Square transformation of your y divided by n minus 1. So we are expecting the distribution of s to be, what's your answer? What is your expectation? What will be the distribution of your s? So y bar will most likely be normal, but what will be the distribution of s? Since it is a quadratic transformation. Anybody?
Chi-square, ma'am.
Chi-square po.
So most likely chi-square, or generalized term will be Wishart, because this is multivariate, no? So we'll see. Okay, so it can be shown expanding this and doing some manipulation of your matrix, that S can be written in this manner. So it is 1 over n minus 1 times the summation of yi prime minus n y bar prime. Okay, so computational wise, in your univariate case, you can remember that one can write this formula as n times the summation of yi squared minus the summation of yi quantity squared, no? Or this is actually if you did not simplify it in this manner, just n minus 1 there, this will be equal to the summation of yi square minus n times the summation of yi quantity squared in the univariate case. So these two actually are equivalent. So this is the multivariate counterpart for this. So y bar will be called the sample mean, and S will be called the sample covariance matrix. So again, S here will be an estimate of your sigma. We do not use the S square usual notation, no, which we know, because this is the usual notation of a variance or a covariance matrix in the sample side. In here, we will just use S for consistency as an estimate of sigma. Okay, wala man taga sigma square. Okay, so that's the only thing here why it is labeled as S. It's just notation wise. Okay. So we will see that y bar and S will be a complete sufficient statistic for the one sample model. So sufficiency, and you will have to show here sufficiency and completeness. Now, to show sufficiency, you have to use the factorization criterion. That is, you just have to look into the joint density function and factor it into two terms. So if you look at the factorization criterion in chapter 1, the factorization criterion tells you that if X has a joint density function F, then Tx is a sufficient stat if and only if. So let me recall it. You can get this from theorem 1.1, which is the factorization criterion. So if your x has a density function, say f x and theta, then we say that a function of this x, so any transformation on x, is sufficient statistic if and only if you can express the joint density function as a product of two functions. One is a function of x and the other one is a function of your statistic, which is a function of x, tx there, a function of your statistic. Of course, the parameter is also in there, in that function. So for some functions, hx and g of the theta. Okay. So this theorem tells you that if you have a statistics t of x, it will be sufficient if and only if you can factor the joint density function into two product. So I think you should be familiar with this from your inference subject. So for easy notation, we will let u be the summation of yi. So it means that 1 over nu will be your y bar, no? And we will let v to be the sum of yi prime, which you will see later that your s here is a function of v. Okay, and it will be a function also of u, because u is the summation of y. So if you look at that, your s is a function of v and u. So since this is the yi's are normally distributed, you use the density function of your normal distribution, which is given by this 1 over 2 sigma. And then this is a joint density function, so it's n times r, no, in your number of factors. And then you have this. So the usual probability density function of a normal that in the univariate case is 1 over 2 pi square root sigma exponential of -1/2 then x minus mu over sigma squared, no? So you know that. And then the univariate the multivariate counterpart of that will be this probability density function. Okay. And then if we try to scrutinize the term inside the exponential term, this one, which is that one, and try to make matrix manipulation there, you will arrive at this term. And then next, we try to look at this term, which is this one. We can insert the trace term here because this term here will be a 1-by-1 matrix, no? So without trace or with trace, they are equivalent because of it's a 1-by-1 matrix. And this is using the properties of the summation and the trace. So we can take out trace outside, and this is a constant with respect to the summation sign. So we put the summation with yi prime. So that notation wise, this is simplified as the trace of sigma inverse v, because our v is the summation of yi prime. So this term here will become the trace of sigma inverse v. Okay, can you still hear me? Am I still clear?
Yes, ma'am.
Okay. So that by substitution now, okay, and using, okay, kini man ang expansion niya, no? And then you apply exponential on both sides of this. So the exponential of a sequence of sums here can be expressed as the products of exponentials. So apply exponential there plus the negative 1/2, you will have this. Are you following? So din nag-apply na tag exponential and then multiply na og negative 1/2. Okay? Are you still with me?
Yes, ma'am.
Yes, ma'am.
Okay, from here na ha, kini. Mag-applyan og exponential times negative 1/2. So exponential of additive terms can be the product of exponentials. So that's why you have this, where this time we use the factorization theorem. So we will have some function of mu and sigma and some function of your statistic t of y. So we see that t of y here will be a component of u and v, no? It is a component of u and v, where u here was denoted by the summation of yi, and v here was denoted as the summation of yi prime yi, or was it yi then yi prime? Let me see, check again. Okay, it's the summation of yi and yi prime. So you can convert the density function into two factors, so that by the factorization criterion or the factorization theorem, which I stated, is u and v are sufficient stat. So we see here that the what we want is y bar and s, no, to be sufficient stat. But what we have shown here is that summation of yi and summation of yi prime are sufficient stats. No, these are sufficient stats. So why can we conclude that from this? Why can we conclude that y bar and s are sufficient stat also? Anybody? Okay, let me iterate again. What we have shown here is only u and v are sufficient stat. And recall that u is the summation of recall that u is the summation of y and v is the summation of yi bar. So actually what we want to show is that y bar and s are sufficient stat. So if we have shown this that these are sufficient stats, these two, what will be the possible reason why we can conclude in the next step that y bar and s are sufficient stat also? Did you understand my question? Hello? Did you understand my question?
Yes.
So what's your possible reason for that?
And function sa I see as a Y bar.
You are choppy. Can you repeat your answer?
Ma'am, function CU ni Y bar. Dayon si V kay function siya ni S. One of the functions.
V and U po sa S.
Okay, so that's possible reason, and that there is one more thing that you have to consider. A very important one is because it is an invertible function. So ibig sabihin, pwede ka mo-add to sa isa. So an invertible function means that if you are given this, you can find this one, or if you are given this, you can find this one. Otherwise, kung dili na sila invertible functions, then it does not follow that any function of this. So kung si summation sa y ay maka-adto sa y bar, pero kung given si y bar dili siya ka-adto sa y bar as a summation of yi, then you cannot say that sufficient stat pod si y bar, no? Dapat it's invertible, bale ma-derive nimo ang isa given ang isa, or the other way around. So that's why it is also a sufficient stat. So in here we see that we concluded that U and V are sufficient stat, and then after completing the completeness proof, morning giingon, this is what I was telling you about. Therefore, T is after the proof of completeness, T of X now will be sufficient stat for the one sample model, and hence UV, this one, since it is an invertible function of T. So bali, makuha nimo si T from U and V, makuha pud nimo si U and V from T. Did you understand? So this is a very important condition here, and it's also complete sufficient statistics. So finally, since it is an invertible function of U and V, that is Y bar and S are invertible functions of U and V, then they are also complete and sufficient. Okay. So to prove completeness, you use the concept of exponential form. So it has to do something with a ball or a sphere that will talk about completeness. So I will not take into consideration the proof of the completeness, because you should have an idea about exponential form. Did you take up in inference about exponential form? Anyway,
Yes, ma'am.
okay, just recall what is the implication for exponential form and apply it in the proof of completeness. So I will not deal so much on that. So the very important thing here is that dako man gud istoryaho ng exponential form. So once you showed that it is a sufficient stat and it is a complete, U and V are jointly complete sufficient stat, and you have an invertible function that can go to your Y bar and S, So value y bar is a function of u, and s will be a function of u and b. And you can go back to u and b being an invertible function, then y bar and s are also complete sufficient step. Okay, so the next theorem, 18.2, tells you that y bar and s are independent. So in here, to show that it is independent, we will use the one that I've always told you, that if you can express your y bar as ay, and you can express your s as y b y bar, y prime, and if you can show that ab is 0, then ay and yb y prime are independent. Okay, so that is how this is proved. And the distribution of your y bar, so from y, I, which are normal, and then you transform it to y bar, it can be shown that it is also normal with these parameters. So ang imong yi is mu sigma yata to, but y bar will be mu and 1 over n sigma. And as what I told you earlier, I was throwing question to you, what will be the distribution of S? You said it is chi-square. Chi-square if it's in the univariate case, but this time it's in the multivariate case. So it will become Wishart with n minus 1 degrees of freedom and sigma equal to 1 over n minus 1 sigma. So let me check first if the denominator of your sigma for S and Y bar is correct from the book. So this is chapter 18. If I don't have any typographical error in that. Yeah. So Y bar is 1 over n sigma and S will be 1 over n minus 1 sigma. That is correct. So this will be the distribution of Y bar and this will be the distribution of S. So on how we will show three things here. One is Y bar and S are independent. Second is the distribution of Y bar, and third is the distribution of S. So this is how we defined our Y. It is a vector where this one is a row vectors because each of the yi's here are terms, no? So actually this is n by r. And then you have a mean vector theta corresponding to the mu primes. So kada isa sa ilaha, yi prime, i-prime niya para pahigda, will have its corresponding mean mu. But actually, they have common means. Okay, so by the previous theorems that we had, if we have a y here, where each of the yi's are normal, the y is also normally distributed. So the mean vector is theta, which comprises of the mu's. And then independence will tell you that your psi is just your identity matrix, which is this one. And there is covariances or associations between columns. So this is just using the result in 17.3. Now we try to rewrite y bar in terms of y by multiplying it by a vector a, no, where a comprises of 1 over n, entries of 1 over n, and a prime is n by 1. So si a ni siya, pahigda iyang orientation so that si a prime will be patindog. Okay? Are you with me? Because a prime here is an element of n by 1. So mao ni ang n by 1. Are you with me?
Yes,
Yes,
ma'am.
ma'am.
Okay, so this is the n by 1. Kana. So what happens here is, since this is your y prime multiplied by this term here, so ay will be something like this: 1 over n, 1 over n, 1 over n, and then prime multiplied by y1 prime, y until yn prime. So multiplying that, you will have 1 over n y1 prime plus 1 over n y2 prime, and so on and so forth. So you will have the summation of 1 over n yi prime. Okay? So it means that your y prime, your y bar will be a vector of the form ay quantity prime. Okay? And n minus 1 times s. So note that your s is defined as, if we look at your s, how is s defined? Your s is defined by this. So it means that n minus 1 s will be defined by this summation here. No? So kini ang iyahang n minus 1s. Kana na term, the summations. Because how okay, so here, ito dapat na ni summation. Ano? Ato man ang gi-derive. I think correct na ni siya. Let us check. Okay, here. Because we have shown that this one is equal to this. This implies that n minus 1 s is the summation of yi prime minus y bar prime. So kulang siya og summation sa first term. Ano naman eh. Ito itsura dito. Sa taas,
Summation of yi prime.
prime. Then, minus.
And opo. And y bar prime.
Okay. So, dapat na ni summation yi prime. Okay. But what is summation of yi prime? That is actually your y bar y. Are you with me? So correct na di. Okay, this is because summation of yi okay, n minus 1 s is the summation of yi prime minus n y bar prime, no? But the summation of I prime can be written as y bar y and then minus this one, so that you can rewrite it in this manner and then factor out y prime in this side and factor out y on the other side. What is left is this is your identity matrix minus n and then a prime here and a. Okay, so what we are looking here is that we can express our y bar as a y bar or y prime a prime, but we do not want this form because what we want is a function of a times y, and then we can write n minus 1 s to be y bar I minus n a prime a y. Okay, so we look at the distribution of this or ay. Look at the distribution of that, which is from the result in 17.2D katong ABC, no? AYB. So wala ni siya identity, AY na lang. So you will have this normal distributed with mean vector A theta because the vector of y, the mean vector of y is theta, and then AI, A prime, and then sigma. So in other words, you have this. Now we look at what is a sigma, a theta. So what is a theta? A theta will just be, ang a nato is 1 over n, 1 over n, 1 over n times the theta is mu prime, mu prime, mu prime. So what you will have is the summation of 1 over n mu prime. And this is a constant with respect to summation, and this is also a constant with respect to summation. So what happens there is you will have 1 over n times the summation of mu prime, which is 1 over n times n mu prime, no? And what is left is just mu prime. So your a theta will be equal to, it's just your mu prime, and a prime will be the summation of 1 over n squared, because your a is 1 over n, 1 over n, 1 over n times a prime was 1 over n, 1 over n, 1 over n. So if you multiply that, that is the summation of 1 over n squared. This is a constant with respect to summation. So you will have 1n times 1 over n squared, or just equal to 1 over n. So that's why it's equal to 1 over n. So that if we look at the distribution of AY, this will be normal with a mean vector mu prime. The A prime here is just 1 over n and sigma. Now, since the y bar with respect to A prime will be equal to AY prime. So if we get the transpose of AY prime and apply what we have in theorem 17.2c. So mu prime man siya, may mga siyang mu prime prime, no? And that is equal to mu. And then the prime man, so mabalis siya. So sigma and n, 1 over n will be swapped. If you recall, pag naa kay y na mu psi sigma, kuhaon mo ang y prime, mu prime sigma prime, sigma psi. Correct? So mo nang mag-swap ni siya lang duwa, but since this is just a constant, you can write it in this manner. Okay? So do you follow? So from here, y bar is expressed as AY prime. So you get the prime of that, the prime of this one. So you will have y bar. And the distribution of y bar is equal to that. Okay? And then we look now at S. Now recall that S can be expressed, or n minus S. N minus S. N minus 1 times S can be expressed as y I N A y prime. Okay. Now we try to scrutinize this term. What is that? Note that in chapter anyway, we know that it is idempotent, but we can prove that. So when we say this is idempotent, then we can show that the transpose of that is just equal to the original matrix, and the square of that is just equal to the original matrix. So we try to check the here, get the transpose of that. So the transpose of each term, but the transpose of I is just I. The transpose of this n is just a constant, so it's just you can take it out, or n prime is just n, so you will have a prime a. So the a here is actually a prime prime, no? Because a b transpose is b transpose a transpose. So that is what happened there. And if you look again, what you obtain, this is actually the inner term there. And for the square, you just multiply that 2 and then do distributive property. You have that. And then this is just a constant, so that is just n square. But if you try to multiply a prime, that is just equal to 1 over n. So what will happen to this term is you will have n na lang, because this is cancelled with one of that. So you will have a prime a. And then this is cancelled out. So what remains is this one, which is actually what is inside there. So we say that the n I minus n a prime a is idempotent. So that if we try to look at theta, theta is your vectors of mu primes, no? This is your theta, vectors of mu primes times this. You see that it is equal to 0. So if it is equal to 0, we say that this is what? Unsa gani ni? This is actually the expectation of this, no? So we are trying to find mu prime mu, or the expectation of this na kini n minus 1s. You get the expectation of this. This is actually the expectation of this yi n a prime a y. So if you get the expectation of that, that is actually this. Okay, ang imuhang y diha is theta prime, kini siya is theta. So what we are looking here is the centrality parameter, which is just 0. So this is telling us that this is a central Wishart. Okay, that's a central Wishart. So the only parameter left here is n minus 1 and sigma. Are you with me?
Yes, ma'am.
This is the centrality parameter, non-centrality parameter. But since it is equal to 0, it becomes central. So there is no delta here. And applying theorem 17.7a, or the one that talks about Wishart, no? So I think that's 17.17a. It will be Wishart with n minus 1 degrees of freedom and sigma. Okay, and then putting this, di ba naman tayo anti-theorem katong the norm sigma, pwede nimo ibalhin na siya sa imuhang parameter. So this part here will be placed with here. That's why it has here. Okay. So ang imong statistic now will be only S. So this is a constant. So it can be shown that it still have a degrees of freedom n minus 1, but the sigma here, okay, naman ay n minus 1. Kung S ra imong gusto, the sigma here will be divided by n minus 1. Because there is a constant there. So kung S ra imong concern, ang mo change lang ana ang sigma, which is divided by n minus 1. Okay. So this is the distribution of your S. So we have shown the distribution of your Y bar, which is normal with mean mu and covariance 1 over n sigma. And we have shown that your S is Wishart with this parameter n minus 1 and degrees of and covariance matrix sigma over 1 over n minus 1. And to show that it is independent, muna to akong gisgot sa inyo ha, that you have to rewrite y as ay, but in this case that is a y prime, and then show that s can be written as b y prime b and y, and show that AB is 0. So ang ato ang A dinhi will be A, and ang atong B will be I minus NA prime A. Are you with me? So mao na ang atong A, mao ni atong B. Okay? Are you still with me?
Yes, ma'am.
Yes, ma'am.
Okay, so if you multiply that, so this will be equal to this. So your A times the identity matrix. Ang sa gani imong A, 1 over n, and then i-multiply nimo sa 1, 1, 1 here. So what will happen is, ang mabilin din puros ragyapon 1 over n, no? Kaya ang entry nimo katura mang mga middle diha. So it's still A. And then if you have that, you know that ang A prime, to kini A prime is 1 over n. So if you have that, that will be n A prime A, but A prime is just 1 over n times A. So this is cancelled. What you have is A minus A, which is 0. So one is a function of AY, and the other one is AY, and the other one is YI minus NAA Y. And since we have shown that A times this is 0, then we say that these two are independent. And since AY can be written in terms of Y bar, and this is actually your n minus 1s, then it follows that they are also independent, so that Y bar and S will be independent. Okay? Any questions? Questions?
None.
Wala raman.
Okay, so we'll have a break, a 15-minute break before we proceed with the next section, which is 18.2. Can you see my slide?
Yes, ma'am.
Okay, so let's continue. We'll have theorem 18.3 in the book of Arnold. So in here, equivalently to, if you recall in your chapter 5, I think, or chapter 6, there is UMV and MLE and invariant estimators for the univariate case. So let me just scan the chapter that talks about MVUE and MLE. So it's in chapter 6. So in chapter 6 in Arnold, you have a corresponding MVUE and MLE estimators, no? So we'll just recall, let me have a space here, okay? So let's utilize this space. So let's do some review. So recall. So if you have a random vector n normal and mu sigma squared I, mu is in some subspace, sigma squared is positive, P is less than N. So your V here is P-dimensional. And then we define a mu hat, which is the projection of Y onto V, and your sigma squared hat is in terms of, or N minus P times sigma squared hat is the square norm of Y minus the square norm of mu hat. So more or less pareha ni siya, no? So you will have Y prime Y minus here na lang kay N times mu prime mu prime or mu prime mu ba to? Anyway, later niya na tayo mag-multivariate. So in here, it tells you that MVUE. So A times your mu hat will be MVUE for A mu. Mu hat is MLE for mu. Sigma hat is MVUE for sigma. N minus P over N times mu hat square. This is hat is what? MLE for sigma square, and there's one more. Best invariant. N minus P sigma hat square over N minus P plus 2 will be best invariant for sigma square. Okay. So now take note, for it to be an MVUE, mu hat has an A, no? You pre-multiply it by an A arbitrary matrix. So, wala tayong makita na mu hat is MVUE for mu in Arnold. No? Wala siya ga specify na mu hat lang, but the mu hat here is unbiased. Okay. So equivalent to this following results, we have an equivalent version for your multivariate case. So here, Y bar as how it was defined earlier, and S are MVUE for mu and sigma. So take note that actually Y bar is an expression of A Y, where our A here is denoted by small a, which is the vector 1 over n, 1 over n, 1 over n. No? So in-ani siya na expression for it to be an MVUE. So we know that it is a complete sufficient statistic, and your expectation of S, which is equal to 1 over n times a function there, after getting the expectation can be expressed as n minus 1 times a function of sigma, which has 1 over n here because of that. So naani na expression after getting the expectation, so that this is canceled out and what we have is sigma. So these two statement is telling us that y bar is an unbiased estimator for mu and S is an unbiased estimator for sigma. So ang katong unbiased estimator katong gi-divide og n minus 1, dili katong gi-divide og n. Now, the Leman-Sheffey theorem tells you that if your estimators are unbiased and it is complete sufficient, and then it tells you that it is MVUE. Okay, so let me state the Leman-Sheffey in chapter 1. That will be theorem 1.4. Okay, am I audible pa? Are you still with me?
Yes, ma'am.
Yes, ma'am.
Okay, so this is theorem 1.4. If your statistic, which is a function of x, is a sufficient stat, is already a complete sufficient stat, no? And then if we can make a new statistic, which is a function of this complete sufficient stat. So remember, our complete sufficient stat was u and v, where u here was the summation of y and v there was the summation of yi. Yi prime, no? Mao na ang complete sufficient stat. So your S of x here is u and v jointly. Your T of S now will be your y bar. So your T of S now will be your y bar and S jointly, no? So if you can make a function of a complete sufficient stat, so your complete sufficient stat is actually this one, no? Kana na function ang complete sufficient stat. And then matransform lang nimo siya into y bar and S. So that will be your T of S. Are you following? So your T of S, if it is already a complete sufficient stat and you can show that this function of your S is an unbiased estimate or an unbiased estimator of a function of your parameter. So in this particular case, you will have mu and sigma. Then the T of S here is the MVUE of tau of theta. Okay. So that is according to the theorem by Leman and Sheffey. So if you satisfy this, then automatic lang. So ang Leman-Sheffey automatic kung mapakita nimo na ang imong statistic T of S, a function of an S which is CC complete sufficient CS, man mapakita nimo na unbiased siya, then MVUE siya diretso. Okay, so we use the Leman-Sheffey to prove this theorem. Okay, so the following lemma will be used to show that y bar and okay, so ang MLE, it's not just S but it's n minus 1 over n times S ang imuhang MLE. So ibig sabihin, if you look at this, man kini siya kay di ba naman ni divisibility by 1/n sa formula, naka sa ibabaw man divided by 1/n. Ibig sabihin, katong divisibility makancel man na. Katong na din i-divide nimo by n mao ang MLE pero dili siya MBUE, no? So if you recall in your statistics journey, there will be two formulas for your S. You are familiar with two formula for your S. The one with katong summation sa yi from the mean square na divide by n, and the other one is katong summation sa yi minus y bar na divided by n minus 1. Do you follow? Kay numdo mo? Na kini usually gamito nato is small s man kini capital S. Do you recall this? Ang isa divide by n, ang isa divided by n minus 1.
Yes, ma'am.
The one that divides these square deviations by n is MLE, but not MBUE. The one that divides this square deviation by n minus 1 is the MBUE. Okay? So this formula here is actually the capital S square, the one divided by small n. Okay, if you look at this, kung imo nang i-scrutinize, ang mabilin ana, ang kato na lang man kini ni ibabaw. Are you with me? Did you understand? Okay, so this is your MLE and this is the proof is shown in the appendix. So here, this is an important result so that you can show that the density function is maximized at this value. So if you can write your density function, so you let U be positive, A and U are R by R matrix or square matrix. Okay, this lemma is telling you if you can rewrite your density function in this expression. So a function of a U, and then you have a U inverse here. Then if you look at this value A here, no? So ang function daw ma-maximize at a value U 1/n of A. So paon lang ninimo kini na value. So ibig sabihin, for example, if you have a probability density that looks like this, the maximum here is here, no? And this is your density function for that. So mao ni ang function. Mao ni ang maximum na nahitabo kung asa maximize ang imuhang function. Kaya na value daw mahitabo na siya dinhi sa 1/n A. Diya siya ma-maximize. No, diya siya taas. Taas ni siya at this value. Did you understand? So mao ni siya ang pasabot, no? Mao ni ang value sa U kung asa siya maximized. Okay? Kaya kini siya mga U values man eh. Man kini siya mao ni ang f of U, mao na image niya. If you plot the f of U, may tabo daw ning maximum at this value 1/n A. So all you have to do is to transform your density in this form. Then kuhaon lang ninimong n. A diha na value, diha ang maximum. Okay. So we will use that lemma to prove that the MLE, the maximum likelihood, will occur on that specific value ng 1/n A. for sigma, no? Kaya masayon siya. And then, so this theorem is telling you as long as this condition is satisfied, y bar will be MLE for mu, and n minus 1 over n will be MLE for S sigma. Okay. So we first show that kini siya is just equal to n minus 1s plus n times this term, no? So we will use this pag abot sa density. If you recall, kana na equivalent, balik ta sa density na itsura ha. Nani man ang itsura sa density, the joint density. Ini. Okay? So nani na term? No? So ato ning ibungkagon sa tangtangon sa nato. And we will rewrite it as kini lang sa atong tan-awon. Kini na term. Okay? Kana. And we will express it in terms of this to solve MLE. Katong sigma inverse, pwede man to inaog. Itong sigma inverse, pwede man to inaog, no? Kay inverse man na. So, may tao na siya, summation of, constant naman na siya over summation. Kana siya over sigma, no? So, may tabo atong density function. Kini lang sa atong tanawon. Unsay porma ana. Okay, so from here to here, it's just operations of your primes. Okay, you apply prime there and then multiply everything. And then since this is a function of y bar, so the technique here is to add and subtract something. No, you are not changing the original form there. Just add and subtract. Are you with me?
Yes, ma'am.
And then after that, adding and subtraction, you join the terms that you want to be together. In this line, it's just a distribution of the summation sign. And then after distribution of the summation sign, this is just a constant with respect to summation sign. So you join this with this. Apply summation here to a constant, you will have n. And the rest here, this is also ang gi-join din ni dili kini but kini because this is minus. And then the rest, this is also n times something, which is this one. And then apply the summations here. Here will be, that will be a constant. And then you write summation of yi, I from 1 to n as n y bar. Okay, so this part here will be ny bar mu prime. And then this part here will be ny bar prime, and then mu and mu bar ny bar prime, no? So mo ni siya. And then this part here will be n mu prime. Is it clear? Is it clear? Did you understand this term from here?
Yes, ma'am.
Okay, very good. Next, as is, this is factoring out n, but this term here by factoring can be written in this manner. So this is what? Special product, no? So pwede nimo isulat siya na. You can check. If you multiply these two terms, it will yield this term. Okay. So now we have expressed this as this. So if we look at the density function now, so this is the density function of your normal, that one times this one. So gigawas lang nato ang sigma inverse there. And then substitute this by what we arrived earlier, because this one is just your n minus 1s. And then you distribute the trace. Okay, the trace there is placed because this is in the multivariate case, no? And then put inside the 1/2. So you have two components. Then you put inside now sigma. Okay, following that, so now we look at this term. So unsa to itsura ganina? So there is no problem with the mu because it is minimized when mu is equal to y bar. Ang ato ang tan-awon is katong lemma, how to apply the lemma. This one for the sigma, no? So if you look at the notes, so to look for the MLA of sigma, this is how we rewrite it in that form, so that this is now your A kana tanan. So 1 over NA. So 1 over NA. So that is 1 over N. A is N minus 1S. So using that lemma, we say that sigma is maximized at this value. So that is your maximum likelihood estimate for sigma. So you just convert this one. So this is not a function of S. So matangtang na siya. So what remains is this one, no? To use the lemma. So if this is not satisfied, you know that in the theorem, we specifically noted there that this should be satisfied. If that is not satisfied, then this is not a positive definite matrix and hence cannot be MLE for sigma. So if this is not satisfied, then the conclusion is there is no MLE. So unless that N is greater than R, there is no MLE for sigma. Okay. Now, to show that Y bar is best invariant, recall that when we are talking about invariant, we have to have a loss function, no? Tama? In your linear models, when we talk about invariant, we should have a loss function. And if we are talking about invariant also, it is associated with some group of transformations, di ba? Then how do we know that it is best gani? Your linear models, how do you know that it is best, gani?
Less than siya, ma'am, compared to other
Nakagam-
estimator.
Less than, what do you mean by less than? Say less than.
Yung variance, ma'am.
Okay, that is how you get that it is best when the variance of it is smaller than any other competing invariant estimators, no? So when we talk about invariance, you have the consideration of a loss function, the group of transformations, and for it to be best invariant, it should have the smallest variance among any other competing invariant estimator for mu. So here we are just looking at the best invariant estimator for mu, and y bar will be the candidate for it, for the best invariant estimator. But it is relative to this Mahalanobis loss function. So it is only invariant with respect to this loss function. So this estimation problem is invariant also. When we talk about invariance, it is only for certain group of transformation. So the group of transformation that is considered here will be G, the G bar. So this is the transformation with respect to the estimator. This is the transformation G bar, transformation with respect to the parameter, and G tilde will be with respect to the estimator. Okay. So we see that the loss function associated with your estimator G tilde with respect to your parameter G bar, if you look at the transformation here under this loss function, so ang transformation niya is just inani, no? Invariant siya, inani lang ang transformation. Ang imuhang y, ang imong y bar, pre-multiplied by a plus, say, a constant. And then if you do that, this is what will be happening in your covariance matrix. May mo siyang ASA prime. So dinhilang na transformation, kining AD plus B. Inani lang pag-transform nimo sa imong estimator. Because if you have this transformation or this translation here, kana, and it will go back to the original loss function, which is this one. So that's why it is invariant. So y bar is the best invariant estimator for mu for the loss function L defined earlier, and under the G bar and G tilde group of transformation. So recall an estimator T hat is invariant under group of transformations G bar, G tilde if and only if you can rewrite your transformation on your estimator, a function of that to be equal to the transformation of the parameter G tilde at this estimator T of D. So that's an estimator T y bar S is invariant if and only if. So kini ang ano, kining T, ang imong G of T will be this transformation A y bar plus B AS A bar, and it is equal to this sa imuhang parameter tilde, no? Parameter at this will be sama imong tilde. Your tilde is something like this. Kini AD plus B. So AD So ang imuhang estimator is your T at Y bar D plus B. So this is your AD plus B. No? So if you can show that that is equal, then your estimator na T, Y bar, and S jointly will be an invariant estimator. So for all A, invertible, and all B. So if we look how the transformation is done, note that T Y bar is equal to Y bar. It picks up the first argument in an invariant estimator. So ang iyahang transformation, katurang kwaon niya ang first argument. Kini na transformation, kwaon lang niya ang first argument, which is similar to this, pero ang imuhang D dinhi is Y bar. So this is equal to the first argument here, but your Y bar is actually your T Y bar S. No, that is the transformation of your estimator. So it means that you satisfy this condition here. So it is invariant. Next, you have to show that it has the smallest risk among all invariant estimator. So you choose a competing estimator. Actually, this is similar to what we proved in the univariate case in chapter. So ano lang yun siya, parallel discussion on the univariate case, which is theorem 6.2. Okay. So if you look at theorem 6.2, that is the parallel proof for Y bar being an invariant and best invariant estimator. Ang dito lang, A mu hatta to be an estimator of A mu. So the flow is similar to that. You will have another competing T, which is invariant. Ibig sabihin, it satisfies this condition. Satisfies this condition. So to satisfy that condition, you have to define some A and B here and do some manipulations so that T of Y bar S will be a function of this. No? And then you look at the risk function of that and express it as two components. One, it's okay, so if you expand, that is equal to that, and you look at the cross products, so I will not deal so much on that. But the flow is to express the risk function in terms of two components. One is a risk associated by the estimator and a risk associated by Y bar. So if you express it that the risk of that is the sum of two components which are both positive, and one component is the risk of Y bar using Y bar. So it means that the risk associated with that competing invariant estimator is greater than the risk associated with Y bar. So you get this conclusion. And since you have shown that for any competing invariant estimator, the risk associated with that is greater than the risk associated with Y bar, then Y bar will have the lowest risk and it will be declared as the best invariant estimator. So go over this proof. The proof here is similar to theorem 6.2. Okay. So next week, we are always talking about y bar to be MLE, MBUE, best invariant, for mu, no? So is y bar the best among the best, no? But according to James Stein, y bar is only good for certain conditions. It is only good when n is at most less than or equal to 2. But when n is greater than r and greater than 2, then y bar will no longer be the best, but there will be a better estimator for y bar, which is called the James Stein estimator. And we will see why, no? So for univariate case, y bar works well. Until bivariate case, y bar works well. But when we have multivariate cases, that is when n is greater than 2, there will be a better competitor for y bar, which is the JS estimator. So until this section here, MVUE invariance, do you have questions?
None, ma'am.
Okay, so if I look at chapter 18,